It's kind of wild when you stop and think about it, isn't it? The air we breathe inside buildings, we just sort of assume it's okay, clean enough.
Yeah, totally take it for granted.
But there's all this this hidden engineering working away quietly to keep it safe.
Right.
So today, we're going to pull back the curtain on something pretty central to that, HEPA mini-pleat filters.
These are fascinating devices, really.
This deep dive, it's all about getting into the nitty-gritty, the science, the engineering that makes these filters work so well. We've looked through the tech specs, performance data, how they're used in the real world, all that stuff.
That's a detail there.
Yeah. And our mission, really, is to show you how they're built to get such incredibly clean air. And, what do those efficiency numbers actually mean for you?
Exactly. And it matters, right?
Yeah.
Good air filtration, it's huge. Think hospitals, keeping patients safe, or even just making offices more comfortable, more productive.
Definitely.
So yeah, we want to help you understand not just what they are, but why they're so important. The clever design, the surprising precision behind them.
Okay, so if this clean air is so vital, you got to wonder, what actually goes into making one of these filters? What are the basic building blocks?
Well, at the core, you've got the frame.
Yeah.
Usually that's extruded aluminum or maybe galvanized steel, something sturdy.
Right. Holds it all together.
Exactly. But the real star, the bit doing the filtering, is the media that's typically a special kind of glass fiber.
Glass fiber, okay.
Yeah. And then inside you find things like hot melt. It's used as a separator.
A separator, what does that do?
It basically keeps the pleats, the folds in the filter media evenly spaced. And you've also got polyurethane, PU sealant, to make sure air doesn't leak around the edges.
Gotcha. Sealed tight.
Right. And that mini-pleat name, it hints at a really smart design choice.
How so?
Well, by folding the media into lots of tiny pleats, they massively increase the surface area of that glass fiber.
Oh, I see. So you get way more filter material packed into the same size box.
Precisely. It's all about maximizing the filtration power without making the filter huge and bulky. Super efficient use of space.
That makes a lot of sense, that clever design. And, okay, talking about performance, this is where all those codes come in, right? EN 1822, HHRAE 52.2. Things like H11, H13, H14, or MRV 16, 17, 18, 19. They look super technical, but they're actually telling us a lot about how well the filter works, aren't they?
They absolutely are. Yeah, they're crucial benchmarks. Let's break down those percentages because they really show the level of precision we're talking about. It's quite amazing.
Okay.
So take an H11 filter. That lines up with MR16. It's designed to capture at least 95% of what's called the most penetrating particle size, or MPPS.
85%.
And for the DOP test that uses specific 0.3 micrometer particles, it gets at least 99.9%.
Wow, okay, that's already pretty high.
It is. But then you go up to H13, which is like MRV 17 or 18. Now the MPPS efficiency jumps to 99.95% minimum.
0.95.
Yeah. And for those 0.3 micron DOP particles, it's 99.99%.
Okay, that's getting really close to perfect.
And then there's H14. Top of the line corresponds to MRV 19. Here you're looking at, wait for it, 99.995% for MPPS.
0.995. Goodness.
And for the 0.3 micron DOP test, 99.999%. Almost everything.
That is staggering, just incredibly precise. So why that 0.3 micrometer size? What's special about that specific number? Why is that the benchmark people test against?
That's a great question. So that 0.3 micron size, it's not just random. Historically, it was considered sort of the trickiest size for filters to capture effectively.
Oh, really? Harder than smaller particles?
Well, it's kind of a sweet spot or maybe a difficult spot. See, really tiny particles, like viruses, often move erratically Brownian motion and actually bump into the filter fibers quite easily. And larger particles, like dust or pollen, are just too big to get through the gaps. They get trapped by inertia or interception.
Okay, makes sense.
But those 0.3 micron particles, they're kind of in between. They don't always move erratically enough, and they're small enough to potentially follow the airflow around the fibers.
Yeah.
So if a filter can grab those effectively...
You can probably grab almost anything else, too.
Exactly. Proving high efficiency at 0.3 microns is a really strong indicator of overall performance. It shows the filter can handle those tough-to-catch particles, which is vital for everything from, hospital clean rooms to just keeping allergens out of your office air.
Right, right. Okay, beyond just the raw numbers, the efficiency. These filters also have some practical upsides, don't they? Things that make them easier to use or better for the building.
Definitely.
Like the specs mention lower pressure drop, which saves energy. They're lightweight, easy to install, and this interlock gasket design to stop leaks.
Yeah, those are all really important practical benefits. That lower pressure drop, that connects directly to energy savings.
How so?
Well, think about your HVAC system, the fans pushing air around. If the filter resists the airflow lower pressure drop, the fans don't need to work as hard.
Less effort, less electricity.
Exactly. Over the life of the filter, that can add up to significant energy savings. And that interlock gasketing, that's critical too.
Why is that so important?
Because even the best filter media won't help if air just leaks around the frame. It needs a perfect seal. That interlock design helps ensure all the air has to go through the filter media. No bypass.
Like closing a window properly so the draft doesn't get in.
Precisely. Guarantees the air coming out is actually clean. And there are other practical points, too. They can handle pretty high temperatures, up to 70 Celsius, and even 100% humidity.
Wow, quite robust.
Yeah, and they meet the UL 900 flame retardant standard, which is an important safety aspect. Oh, and the specs mention a recommended final pressure drop to maximum 500 pascals.
Okay, 500 pascals. What does that actually mean in relatable terms? Is that a lot of pressure?
Good question. 500 pascals.
Yeah.
It's not a huge amount of pressure in everyday terms. Think maybe. The pressure exerted by a stack of about 5 sheets of standard paper on your hand spread over a square inch, or like a very, very gentle breeze.
Okay, so pretty subtle.
Yeah, it's a measure of resistance. So the final pressure drop recommendation means that's the point where the filter is considered fully loaded with dirt and needs changing because the resistance has increased that much. Starting lower means it lasts longer before hitting that limit.
Got it. That helps picture it. And speaking of pressure and airflow, we saw this really interesting graph. It plots pressure drop against face velocity for the different filter grades, H11, H13, H14.
Ah, yes, those performance curves.
What does that graph really tell us about how they behave?
Well, it visually confirms that connection between efficiency, airflow, and resistance we've been talking about. Face velocity is just how fast the air is moving through the filter material itself.
Right, meters per second.
Exactly. And the graph shows pretty clearly that as you push air through faster, increase the face velocity, the pressure drop, the resistance also goes up for all grades.
Makes sense. Like trying to drink faster through a straw, it gets harder.
Good analogy, yeah. And you'll also notice on the graph that the lines for the higher efficiency filters, like H14, are generally above the lines for H11 or H13.
Meaning higher pressure drop for the same airflow?
Correct. At the same face velocity, the H14 generally has a higher initial pressure drop because its filter media is denser, finer. It has to be to catch those extra tiny particles. It's doing more work.
So there's a trade-off. Higher efficiency means slightly more energy needed to push the air through, initially at least.
That's the balance, yes. It's about finding the right filter grade for the specific need, balancing the required cleanliness level with energy consumption. Oh, and the graph usually notes a tolerance, too, like plus or minus 10% on that pressure drop value. Just accounts for manufacturing variations.
Okay, so putting it all together, what does this mean for you listening right now? Where are you actually likely to run into these kinds of high-tech filters?
Well, these high-efficiency filters, they're really crucial in places where air quality is absolutely non-negotiable. So think healthcare first hospitals, operating rooms, clinics.
Makes sense. Protecting patients.
Absolutely. Preventing the spread of airborne infections is critical there. But also in commercial buildings, offices, schools.
Schools, too.
Yeah, definitely. Better air quality can mean, fewer sick days, better concentration for students and teachers. And then in industrial settings, too, clean rooms for manufacturing electronics or pharmaceuticals, labs, places where even tiny particles can cause big problems.
So quite a wide range of places.
A very wide range. And the great thing is they're not one size fits all. The specs show a huge variety of standard sizes, like 12 by 24 inches, 24 by 24 inches, different depths.
Right, I saw the tables. Specific dimensions, airflow rates listed for each size and grade. Like 0.56 cubic meters per hour for an H13 of a certain size, 0.58 for an H14.
Exactly. And different initial pressure drops, like 140 pascals for that H13, 145 for the H14. Even the total media area is listed, sometimes hundreds of square meters packed into one filter.
Hundreds, wow.
Yeah, thanks to those mini pleats. And it even mentions customization as possible, special sizes if needed, and different sealing options like a gasket seal or a gel seal, depending on the application's specific requirements. Really flexible.
So we've really peeled back the layers today on these HEPA mini pleat filters. It's kind of amazing, isn't it, how these well,
Mm.
seemingly simple boxes
Mhm.
are actually packed with really sophisticated engineering.
Mhm.
All that precision, that incredible efficiency, playing such a vital part in keeping the air safe inside so many buildings we use every day, these silent guardians.
They really are. And maybe, this brings up an interesting thought to leave you with.
Oh, yeah.
As you go about your day-to-day, maybe moving between your home, your workplace, maybe a shop or a clinic,
Uh-huh.
just pause for a second. Think about the air. How might actually being aware of the air quality and the hidden systems like these filters working constantly to maintain it,
Yeah.
how might that change how you perceive those spaces?
Hmm. That's interesting.
It's just a reminder, really, of all that unseen effort, that technology that's quietly working away, looking after the quality of something as fundamental as the air you breathe. Makes you wonder what else is working behind the scenes, doesn't it?